In other words, so it's the first parent that I am at his left, okay? Because if I am at the left of this parent, this means that this parent has a value greater than my value. Okay, so 9, for example, is at the left of 13, which means that 13 is greater than 9, and 13 will be actually then the successor of 9. Similarly, for example, 2 is at the left of 3, which means that 3 is greater than 2, which means that 3 is the successor of 2. Okay. 4, for example, is 4 at the left of 3 is the parent of 4. Is 4 at left left side of 3? No, this means that 4 is greater than 3, and 3 is not the successor. Then we would go and look for the grandparents of 3. Is 3 at left of 6? Yes, which means that all the elements 3 and 4 are less than 6, and since 3 is not less than is not the successor of 4, then 6 will be the successor of 4. Okay. Similarly, for example, for the element 13, 13 is at the right of 7, so 7 is not a successor. 7 with the 13 are at the right of 6, then 6 is not the successor, and these values are greater than 6. 6, 7, and 13 are at left of 15, which means that they are all less than 15, then 15 is the successor of 13. Similarly to the 17 here, for example, 17 is at the left of 18, then 18 is the successor. Okay, etc. So this is how we find the successor. So it's either if there is a right child or right subtree, then we will find the minimum of this right subtree, and this will be the successor. And if there is no right, we'll just go up until we find a parent or a grandparent that we are at his left. Okay, and this will be actually the successor. And this is actually the algorithm. So if right x different from null, so there is someone at the right, then we will just take the subtree where the right x will be the root and find the minimum of this and return the minimum value. Otherwise, we'll say, okay, let's assume that the parent of x is y. If the parent of x is different from null, which is normal, and if x is at the right, so if x is at the right of its parents, then we will go to the grandparent. If x is not at the right, so if x is at the left and this is false, we will simply return y. And if x is at the right of its parent, which is y, then we will just do x is equal, put y in x, and y will be the parent of y, so we'll go one level up. Okay. And similarly, the predecessor is similar, but with a little bit differences, and this can be a question that you have to answer. So this is actually the explanation. So if the right subtree of node x is non-empty, then the successor of x is just the leftmost node in the right subtree, which is the minimum. And we can find this by calling the function tree minimum, where right x will be the root. If the right subtree is empty, then x has a successor y, and y is the lowest ancestor of x, whose left child is also an ancestor of x. So this means that we'll just go up until we find that we are at left of our parent or grandparent. Here is a theorem regarding the analysis of the performance of the operation we have seen. So the dynamic set operations, which are search, minimum, maximum, successor, predecessor, can be made in OH time, where h is the height of 3, because we in all the algorithms, for example, this algorithms we cannot go more than we cannot go more than the height of the subtree. So the while will go at maximum, or the while loop or the repetition will go at maximum the height of the tree. Okay. So this is regarding the successor and the predecessor. Now let's talk about the insertion. Okay, so the insertion, if you want to insert an element inside the tree, then where to insert this element? We need actually to go left and right until we find the right place of the element. Let's first consider the node Z. Actually, we have a node Z. Any node to insert in a tree will have a parent. So the parent address will be in this area. Then the key, which is the value of the node, will be in this area. The pointer or the address of the left child will be in this area, and the address or the pointer to the right child will be in this area. Okay, so this is simply, you can see this as object. This will contain the reference to the right child. This will contain the reference to the left child. This will contain the reference to the parent, and this will contain the value, for example, an integer, a character, or whatever. Now, if this node Z, we want to insert it and inside this tree, for example, let's say the element 13. So, or let's say, for example, the element, any element in this tree. The idea is to say, okay, for example, let's say let's assume that we are at this element 18, and we have the Z, and we don't know where to put the Z. So what we should do actually to compare the key of Z, which is, for example, let's say 13, to the key of X, which is 18. So if key of Z is less than key of X, we need just to go left. Otherwise, we need to go right. Okay. And similarly, 13 here, when we are at 15, we just check key of Z, which is 13, is less than or equal key of X. The answer is yes. Then just X will be equal to left of X. And we keep continuing until we find that X is equal to null. When X is equal to null, for example, here, X is 15, left of X is, okay, here we inserted actually the 13. So originally there is nothing here. So left of X is actually null. Okay. So what does it mean left of X is null? It means that I have to put Z at the left of X. Okay. This is actually how we would do. So the algorithm is the following. We start by X equal to root T. So here, if we want to insert 13, we start with the root. And then we say while X different from null. So at the root here, X is different from null. What we do, we just say Y is equal to X. This is actually to save or to track. And then we say, is key of Z less than key of X? Here, for example, we will find out that yes, key of Z is not less than key of X. It is greater than. Okay, what does this mean? This means that we need to put X now is equal to right X. Okay, what does it mean here? So X will be equal to this node. Then we check, is X different from null? The answer will be yes. Why? Because 18, this node is different from null. Okay, so what we do here, we just say okay, Y is now equal to X, which is the node 18. Then is 13 the key of Z less than 18? The answer is yes. So 13 that we want to insert, which is the Z, is less than 18. What does this mean? This means that we need to go to now X will be equal to left X. Okay. So X is equal to left X. So X is now this element here. So is X different from null? Because we are still in the loop of the repetition. So yes, x which is 15 is different from null. So what we do, y equal to x. So what does it mean, y equal to x? It means that now it means that the node 15 here will be put in y, and then we will compare key of z to key of x, and x is still the 15 here. So is 13 less than 15? The answer is yes. So it is less than 15. What we will do then, x will be equal to left x. Okay. X is equal to left x, then x will be equal to null. There is nothing here. Okay. Now what we do, is x different from null? No, x is equal to null. Then here we are done. So what we have right now, we have that x is now null, y is the 15 here, the node 15, this is actually y, and now we need to insert x at the left of y. Okay. So we say, okay, y, the parent of z, which is the parent of z now is y, which is the 15. Okay. And now here we check if y equal to null. Why do we check this? Because if y is equal to null, this means that from the beginning x was equal to null. This means that actually x was is the root, because here y null and x root. If the root is null, then there is nothing. Then what we will do, just put z is the root of t, because it might happen that there is nothing inside the tree. Okay. In this case, we'll have y equal to null and x equal to root. Then we put root t. So x equal to root t, and root t is null. Then we'll just put root t is equal to z. If the tree is not null, so there is a root, there is elements, then in this case, what we will do, we will again check, because we need to know whether z should be at the right or at the left of y. So if key of z less than key of y, then left y is equal to z. So we'll put z in left y, and otherwise we'll put z in right y. Okay, because actually we need, when we insert an element, we need to update. What does it mean to insert an element? To insert an element, we know that the left of this element will be null, the right will be null, because this is an element that we insert, so it will be inserted at leaf. The parent of this element, the key of this element, we have at 13. The parent of this element needs to be updated with the 15 here, and the left of the 15 should be updated with the 13. Okay. And this is what we do actually here. Okay, so this is regarding insertion. The next we'll talk about how to delete an element from a tree.